Our next speaker is Ms Renuka Sahu. She is a PhD scholar from NMCAD Lab. Her work is on carbon nanotubes and their composites, including developing higher order VAM-based strain gradient theory to include small size effects in nano and microstructure. She has also received the much sought after IISc Industrial Fellowship, as part of which she successfully completed a year-end of internship at Airbus Defence and Space GmbH, Munich, Germany.
So I will be talking about the combination of variational asymptotic method and the strain gradient theory, which is a modified approach to the classical continuum theories which we use. So moving on, I would start off with a basic introduction, then define my objective and what are the methodology which I'm using and some preliminary results, giving you the conclusion and the future scope. So we all know continuum mechanics, as we are all structural engineers here. We know that continuum mechanics goes by the assumption of that a body is not, it's a continuous material. There is no distinction and it treats the body as a continuum. Continuum means continuous and homogeneous substance or material, which can be described by smooth functions and equations without reference to individual atoms or molecules. So even the classical elasticity theory, it derived the stresses using this assumption that stresses at a point in a body depends only on the strains at that particular point. So that's why we have this classical law, which is the Hooke's law. And this theory, it's applicable to mainly meso and macro length scales. Of course, we use it for other applications as well, but there comes in more parameters which start to affect the behavior of the material, which is not accounted by these theories. So as we all know, all existing theories, they are derived from this particular approach, be it Euler-Bernoulli beam theory or Timoshenko beam theory. But as we moved on to materials like composites, which include carbon fibers and smaller structures, and as we began to go through the micro scales, we began to observe some rotations or some displacements, which again, they were giving some kind of non-linearity, which could not be completely justified by this theory. So here we have that in reality, the materials, they are composed of atoms and molecules, which again are a separate entity and they interact among themselves, leading to the forces and strains, which affect the continuum and the macro scale. So for this particular, all the theories, even for VAM, which we have, it is completely applicable for macro scale models. So moving on, we have non-classical approaches. So non-classical approaches, they again include various different ways in which we can identify these parameters which affect the stresses and strains. So again, we have non-local theory, which was given by Ehringen. Then we have higher order gradient theories, which include modified couple stress theory and strain gradient theory. And then again, a new approach is coming up more recently nowadays. We see that non-local strain gradient theory, which combines both non-local theory and the higher order gradient theories. So we have non-local theory. So in this theory, Ehringen removed that assumption that we were going by, that stresses at a point depend only on the strains at that particular point. He again redefined the stress as using a kernel function, which takes into account that the stress is not only dependent on that location, but it also depends on the deformations around a certain area, so different points are also affecting the stress at that particular point. So this is the basic integral form of Ehringen's equation, which by employing this kernel function and this parameter, which is basically the non-local parameter, it is the internal length scale parameter. So it will include all this atomistic effects, which will affect the overall stress. Then we have the higher order gradient theories. So these theories, they use a modified strain energy expression. So just for classical theory, we have this expression that half sigma ij epsilon ij. But moving further with the strain gradient theory, what happens is we are not only including the strain, but also the gradients of the strain to more effectively capture what is happening at a microscale level. So here we have more higher order terms, which include the gradients of the strain multiplied by the corresponding stress tensors to get the higher order strain energy. And then now what is being come up is the combination of both these theories, which is that you take the material parameter from the non-local theory as well as the gradient, the strain gradients and their effect. So that's why here this definition will give us it comes from the non-local theory by Ehringen. And here we have the L, which is the material length scale parameter. And there is the gradient of the strain, which comes from the strain gradient energy expression. So it is seen that by using these theories, now we can get more closer to the results at microscale and even nanoscale to say. So why are we going for a non-classical approach? As I said, materials, as we know, they are made up of atoms and molecules, which have some intermolecular interactions. So classically in continuum mechanics, these interactions, they did not used to have that much effect because we used to take some meso structures. But going to the now that we are looking for a carbon nanotube composite or even including graphene or other nanoscale materials, even microscale materials, we need to consider these intermolecular interactions, which can in turn affect the overall macro scale responses of the structure. So definitely the basic assumption of stress locality fails for smaller length scales. So we need to add that to the existing continuum mechanics. And materia is not a continua in reality. And various attractive and repulsive forces exist between these entities and they affect the deformational behavior. And also when we look into some highly nonlinear phenomena like plasticity and fracture, there also the crack, it's very small. So we have to again consider that the effect of these parameters in the vicinity of the crack or even for plasticity applications, these approaches come in handy. And instead of going for these molecular dynamics or molecular mechanics approach, which they are good for and very good and very accurate for smaller structures existing only at nanoscale or microscale. But if we want to extrapolate those results to a X structure like some aerospace structure or composite, then it will take a huge amount of computational effort and time. So instead of doing that, we can go for this approach. So we have atoms, molecules, compounds, which make together the material. And starting from nanometers, going to micrometers, we can achieve these responses at the millimeter level. So the objective here is to obtain a higher order beam model by capturing the length scale effects inherent in the micro and nano structures. So I would like to give an overview of some beam theories, like classical theories like Euler-Bernoulli beam theory, which takes into us the assumptions that the plane sections, they remain plane even after the deformation, and the sections remain normal to the bending reference line. So these assumptions, they helped us to identify the local deformations and displacements in the beam, but they were not accurate if we move on to the nonlinear analysis of material and the structure behavior. So that's why Timoshenko, he modified the Euler-Bernoulli beam theory by relaxing the normality condition. He introduced a shear force effect as well. And then we also have higher order beam theories like shear deformation theories and other higher order formulations, which incorporate the shear correction factor either using trigonometric expressions or exponential expressions. And we have VAM-based theories, which is given by Berdichevsky. So the advantage of VAM-based theories, as we have already seen with all these talks, and the audience is now well aware that VAM-based theories, they do not involve ad hoc assumptions which are involved in the classical theories. And they are applicable for highly nonlinear problems. We can easily use them to obtain the whole 3D deformation behavior of the structure, which might not be possible as accurately with the other theories. And again, if we are able to generate a completely extensive VAM-based beam theory, it will help in saving a lot of computational cost and time. Because if we go for FEM models or we go for completely suppose in case of nano or microstructures, if we go for molecular models, it will take a huge amount of time as well as cost. So moving on to some literature, Mindlin, he was the one to develop the strain gradient theory. He identified that apart from the classical Lame's constant, we also have other elasticity constants corresponding to the different strain gradients. So in total, he identified that there are 5 elastic constants which will define the whole constitutive behavior of the material. Then they came Lam et al. Who reduced the material parameters for isotropic materials from 5 as given by Mindlin to 3. And again, using non-local strain gradient theory, we have that we can obtain the shell model formulation for buckling study of CNTs. So this formulation, as of now, it gives a very good correlation with the molecular dynamics results observed. You can see this in the this graph that we have the critical buckling load, and we have results from various theories, including molecular dynamics and non-local and the combined non-local strain gradient theory. So it is seen that the molecular dynamics and non-local strain gradient theory, they are in very good correlation. And here we have the bending rigidity defined for using a strain gradient approach and using the classical approach, that how upon increasing the thickness to the length ratio, we have that the strain gradient theory, it gives a very high bending stiffness compared to the classical theory for smaller thicknesses, and it converges to the classical theory as the thickness is increasing, meaning that as we go for smaller length scale of the materials, the effect of strain gradient becomes more predominant. And also, there has been use of non-local theory for elastic modeling of CNTs to obtain the stiffnesses of CNTs. So in this graph, you can see that there have been models for chiral and achiral CNTs, and it has been seen that using non-local theory, we can obtain a good stiffnesses values as comparable to the molecular simulations. Then we have also seen that the strain gradient theory, it can be used to for the study of dynamic problems in microbeams, and non-local theory, it has been used to obtain these stiffnesses, as well as they are used for bending and buckling studies. So again, here the critical buckling load, as you can see in the graph, that we have the classical theory where these length scale parameters, they are taken to be 0. So classical theory, it is giving a very low buckling load compared to the strain gradient theory or coupled stress theory. So again, this thing is dependent on thickness. So as you go for a smaller beam thickness, you see that the differences are very much higher in between classical theory and the strain gradient theory. And for bigger thickness values, these differences are not that much. So coming to carbon nanotubes, because these are what we are currently trying to use and incorporate more and more because of their very good structural properties as well as other multifunctional properties. So they are recently discovered wonder materials by Lijima in 1991. So carbon nanotubes, they are either single walled, double walled, or multi walled, depending on the number of concentric tubes there are combining to form a structure. So they have very high Young's modulus, high tensile strength, and they are light in weight, and they have a high aspect ratio. So being light in weight and having such good structural properties, they become very important for potential application in aerospace structures. So aerospace basically focuses that we need to have lighter materials, but stronger materials, so that we can have a greater fuel efficiency and we can have a longer range for aircraft applications. Also, there are other advantages to carbon nanotubes, like they have superior thermal properties, very good electrical properties. So these make them good for multifunctional applications. Apart from that, there is an added functionalization which is possible, meaning that instead of just having a carbon nanotube composed of only carbon atoms, desired to your applicability, you can introduce some functionalized groups, which will in turn help carbon nanotubes to adhere to some polymers more efficiently, and maybe even for some biomedical applications and NEMS applications, they can be used. Then again, we have seen that there are electromagnetic shielding applications, and there are also studies which try to estimate the application of carbon nanotubes to structural batteries. So here are some properties of the single wall carbon nanotubes, where the thermal conductivity is very high, around 1000 to 4000 watts per meter Kelvin. The tensile strength is 90 to 120 gigapascal. The Young's modulus is around 500 to 1 terapascal. And the electrical conductivity, which is very, very high if you compare to the other conventional materials which we use in aerospace applications. Then here, this is a schematic which shows that how we can use carbon nanotubes in structural batteries. So here it's basically structural battery was also talked in a previous talk where it was told that the structure itself, the composite structure itself acts as a battery. So that is achieved by having two different laminates in which one laminate, the fibers will act as cathode and the other which will act as anode. So to have a better intercalation of the ions which help the electrochemical reaction, we can use carbon nanotubes which are grown onto the surface of the fibers. So they can help to achieve, again, good electrical properties. They can help to improve the fiber properties. And they can also help to adhere the ions more more strongly to the fiber, giving more electrochemical capacity. There's also a work which shows that if you have fibers which are reinforced with multi-wall carbon nanotubes on their outer structure, and you take it through a charge-discharge process, this is how the carbon nanotubes behave upon charging and discharging. They will help to increase the surface area, and they will help to increase the reaction rate as well. So we have some literature for carbon nanotubes where it is shown that the local buckling of carbon nanotubes under bending was studied using molecular mechanics. So in this work, they were able to demonstrate the formation of a kink and sudden drop in stiffness upon buckling. Again, there was also a study of carbon nanotubes under torsion using continuum elastic shell models. So in this also, the nonlinear load deflection behavior and load and torsional angle curves, they were obtained, and unstable post-buckling paths using continuum models could be obtained. And Silvestre, they studied the buckling of CNTs under axial compression, bending, as well as torsion using FEM and atomistic-based beam theories. So they highlighted the importance of geometric parameters of carbon nanotubes on the critical load and strain measures. So here in the figure, you can see that how upon increasing the load, you can see the deformation of the cross-section of the carbon nanotube, which initially was circle, it slowly deforms and takes a dumbbell kind of a shape. So this cross-sectional deformation affects the overall stiffness of the carbon nanotubes, leading to a lower bending load or a buckling load compared to what the classical theories could predict. So this is an estimate of the kind of modeling methods which have been used to study the elastic properties, bending, buckling, and failure. So we can see that a lot of work has been done using molecular dynamics, molecular structural mechanics, and FEM. And few works now are involving non-local models as well. But again, in buckling and failure models, there is a less contribution from the classical approaches or the non-local approaches. So there is a literature gap there. So now there are few ways to use CNTs in a composite. So one of the most commonly used method is the matrix modification method, where we just just put CNTs into the matrix and just stir it up, and it's the most common way to use it. Or we can graft onto the carbon fibers. So here we can see the center fiber, which is the black fiber. It is the carbon fiber, and around it, along the radial direction, we have the carbon nanotubes reinforced. So this method, it helps to give a lot of added functionality to the carbon fiber. It helps to improve the transverse properties mainly because of the reinforcement along the transverse direction. So you will have more better transverse moduluses, as well as the properties, thermal properties, electrical properties along the transverse direction. Then you can also introduce CNTs, align CNTs in between the laminate. Again, this has the advantage of improving the interfacial shear strength, the delamination, and the fracture behavior in the composite laminates. So again, some literature again for the carbon nanotube composites, where we can see that they give elastic property improvement in transverse elastic modulus, as well as the tensile strength, yield strength, and flexural strength. Even for failure, damage, and delamination, it is seen that there is an improvement in fracture toughness as we increase the CNT volume fraction in a matrix. And again, CNT engineered interfaces, they help to improve the fracture toughness of the composite and improve the interfacial shear strength, because CNTs bring in a huge structural added functionality. And also impact loading has been affected by using CNTs. So here you can see a figure which shows that how the fracture crack could be arrested by the use of the carbon nanotubes. So also coming to the multifunctionality part, we have that it can help for lightning strike protection, electromagnetic shielding, piezoelectric sensors, as well as thermal applications. So here, this is a lightning strike area, giving the temperature distribution on the lightning strike area. So this is a normal CFRP, and this is a CFRP which uses the carbon nanotube reinforced carbon fiber. So you can see the temperature distribution difference here, which shows that the damage due to lightning strike can be minimized by using the carbon nanotubes. Also, the electrical conductivity, thermal conductivity, all these properties, they have shown a huge amount of improvement, if we can see from the graph, by using interface modification done using carbon nanotubes. So in my work, I'm using carbon nanotubes, and the methodology which I'm trying to use here is the variational asymptotic method. As you all know, variational asymptotic method, it combines variational methods and asymptotic analysis. So the good part of VAM is that it uses small parameters which are inherent in a problem. So we have to identify small parameters present in a problem and use it to study our formulation. And VAM has been used for study of beams, plates, shells, as well as for homogenization. So the main concept here is to go for minimization of the strain energy functional and then carry out an asymptotic analysis at the strain energy level. So order analysis, it forms a very essential part of the model development. As we identify these small parameters and do the order analysis at this strain energy level. So using this, we can capture geometrically nonlinear behavior like brazier effect and trapeze effect, which are observable in thin wall structures. Like brazier effect, we can see as the in hollow thin wall circular cross sections. So what happens is the cross section ovalizes as we increase the bending load. So upon increasing the bending load, the cross section also deforms, which is not usually captured in classical models. Similarly, in trapeze effect also, it is for strip-like beams. So there also the deformation of the cross section is captured. So again, this model can also be applied for studying multifunctional effects like piezoelectric effects, delamination, electromagnetic effects, and other properties. So this is a basic approach which we follow during the VAM. So we have the cross-sectional geometry, we have the 3D elastic constants, and we go for the 2D cross-sectional analysis first. So using the kinematics in the problem, we derive a 2D cross-sectional analysis a definition of these strains, and then we obtain the strain energy functional. So using that, we can obtain the strain in the warping and the strain recovery relations. Again, once we have obtained the warpings, we can carry out the 1D beam analysis, using which we can get the 1D generalized beams, strains, and stress resultants. And then carrying out a 3D recovery analysis, we can have the 3D strains and displacements. So here is a general beam coordinate system. So we have the undeformed state and we have the deformed state. So the reference line here is used to represent the beam. So we have these coordinates x1, x2, x3, where x1 is along the length and x2, x3 is along the cross section, and the associated unit vectors. So we have the local coordinate system for the deformed state. We have the local coordinate system for the undeformed state. So y1, y2, y3, again, it is corresponding to the x1, x2, x3 directions. But at the local level. And then similarly for the deformed state also, we have these cross-sectional coordinates and the basis vectors. So relating the deformed and undeformed position vectors, we can get these relations. And using this, we can obtain the deformation gradient tensor using the contravariant and covariant vectors. So once we get this, we can move on to our 3D strain, where using the 3D, this deformation gradient tensor, we can get the 3D strain tensor. And here I have shown the deformation gradient tensor for a hollow cross-section tube. You can get different for different cross-sections. So this is the, now using the strain, we can get the 2D strain energy. And so now we have to define what is the order in our problem. So basically, we have to identify the small parameter. So small parameter can be either geometric or physical. So depending on the different cross sections, like for rectangular cross sections, the small parameter is basically the width on the length. And the circular cross section, if you want to draw a solid circular cross section, you can have a radius to length ratio as a small parameter. Then for strip-like cross sections, where even the thickness to the width ratio, it becomes another small parameter. And similarly for thin hollow cross sections, we have the thickness to the radius ratio, which again becomes another small parameter. And then we always have this strain as the small parameter. So dividing the strain energy functional, the strains in terms of these small parameters, and retaining the terms in the orders of these small parameters, we carry out the analysis in different steps. So first we carry out the zeroth order analysis, which includes just the leading order terms extracted from this strain energy functional. And then we use the variational formulation, where we minimize the zeroth order strain energy functional with respect to the unknowns, which here for our case are the warpings. And then we get the Euler-Lagrange equations and the associated boundary conditions. And we use the Lagrange multipliers to enforce some global constraints. So here, these global constraints, they basically depict that there are no contribution of warping to the general deformation due to extension or due to bending or due to torsion. And using these, applying these constraints and from the solving the governing differential equations, we can get our warping solutions. So this is a general zeroth order approximation flow, where we get the position vectors, we get the contravariant and covariant vectors, and we obtain the deformation gradient tensor. And then we get the 3D strains, again doing the order analysis and getting the strain energies, minimization and solving equations, and then again the warping solution. Now, if you want to move on to a higher order approximation, we need to perturb these warping solutions, meaning having a higher order term for the warping approximations. So then those perturbed warping solutions, they are again substituted into the 3D strains, where again we will segregate a strain energy functional in terms of these orders, and we will now include a order higher. Now we will include U0 plus U1, so that we include this term which was initially not taken. So using this, again, we'll carry out this same process and we'll get a higher order solution. So we can go on for as many iterations as is required for a problem. Now moving on to the 1D analysis part, we have the 1D nonlinear analysis using finite element approach. So here we use the mixed variational formulation, where we have the strain energy per unit length of the beam, the whir, as well as the action at the boundaries. So using this, we can get the force and moment relations as follows. Okay. So yeah. So for the gamma and kappa, which are the generalized 1D strains for extension and the bending curvatures, we can use these kinematic relations, where C is the rotation matrix containing unknown variables, and theta, gamma, and kappa are the generalized 1D strain and curvatures. So using these relations and substituting them in the weak formulation, we will get the generalized forces and strains to the constitutive law as follows. So we have the stiffness matrix, which is again dependent on the material and the geometry of the structure. And we have the internal forces and moments. So from this, we can get the solutions for the gamma and kappa in terms of the other measures. And here, the actuation forces and moments are also accounted. But for our case, since we are not taking into account the dynamic study, we will ignore those effects. So now the beam is discretized into n number of elements. And by using some simple linear shape functions, we can get a set of non-algebraic equations. So where we'll have the structural component and the load operator, and x is the unknown vector containing all these structural variables, which is given as follows. So here u, theta are the displacements, and f and m are the forces and moments for different elements. So this is a basic, you can say, structural and load operator matrix for a complete set of n number of elements. We can specify what kind of boundary conditions and forces and moments which we want, and using that we can obtain our displacements and rotations. So yeah, so I first tried out a simple CNT beam formulation in which we just did the 0th order solution, and we started by modeling CNT modeled as a hollow cross-section beam. So this was the beam coordinates which we had taken. So for this model, we only considered the R by L small parameter, and a simple strain formulation was used. So we got a very simplified 1D beam formulation, and we used fixed tree boundary conditions just to get an estimate of the CNT displacements and rotations, and how well we can capture using the VAM formulation. So here, the effect of cross-sectional warping and the localized deformation, it was not that extensively captured in this model. So we could just try out some simple tensile loading and torsional loading, where we could get very simple results as possible with any classical theory. So this was just to examine with what extent we can go with the CNT formulation. So moving on, we went to the study of buckling of CNTs using VAM. So what happened is, now here, instead of taking a very simple approach, we are now including the small parameter h by r as well, which again affects, includes non-linearity in the problem. So here we do the VAM analysis up to first order. And what we see is that there is a non-linear bending stiffness, meaning that the bending stiffness is not independent of the curvatures. So as the beam curvature changes, your stiffness also changes. So there is a complete to and fro of information between these two parameters. So that affects the cross-section as well. So your cross-section deforms, your stiffness changes. So you have to completely iterate and update the solutions to get a non-linear formulation. And then the effect of this non-linearity on buckling loads was captured. So again, we use the fixed tree boundary conditions, and these were the CNT parameters taken. So here we can see that we have subjected the CNT to an axial compressor load, and we plotted the transverse displacement versus the axial load. So as you can see, there is a point A at which, after which the deformation is huge and the increase in force is not that much. So this is the point where the buckling starts, meaning that your structure has started to fail somewhat. So at this point, we have obtained the cross-sectional deformation as well. So this blue here, it represents the undeformed configuration, and the dashed line, if you can see, it represents the cross-section at point A. So we can see that at buckling onset, there is a very slight change from the circular cross-section. Moving on to post-buckling loads, which might be like somewhat near to the buckling load, but the deformations are huge. So we see that the cross-section has ovalized a lot. It is now an oval kind of a shape. And another post-buckling shape gives a dumbbell kind of a shape for the cross-section. And beyond this, I don't think we can apply any force because the material has failed here. So again, we also try to get some combined loading cases. So here we have the buckling load plotted with respect to the radius to thickness ratio, showing that how these geometric parameters affect the buckling load and affect the cross-sectional ovalization of the CNT. So as we see, for a smaller radius to thickness ratio, the buckling loads are very high, and there is not much ovalization observed. the dashed line, the red dashed line will give the ovalized cross section, and the blue one is here giving the undeformed cross section. So we are comparing two different models here. One which does not take into account this non-linearity, which does not take into account the non-linear bending stiffness, and the one which considers that there is a change in stiffness at each deformation step. So we can see that there are lower buckling loads in reality if we take into account the change of bending stiffness and the cross-sectional non-linearity. And as we see, the radius to thickness ratio, meaning that the changes in thickness, they affect this non-linear behavior a lot. As we go for a higher radius to thickness ratio of 100, there is a huge difference between this buckling loads obtained as well as the deformation shape. You can see there is a huge ovalization here. So this was what we wanted to capture using this model. Again, we also validated it with a few results from FEM and molecular dynamics as well as non-local result. So we could see that this model could capture the buckling phenomena quite effectively compared to the MD and non-local models. And we also considered another combined loading case of twist and compression, where the CNT is twisted first and then a axial load is applied to it, as given by Youngage et al. So there also we could capture essentially the buckling phenomena. Now coming to the strain gradient theory. So far, we have seen that we could capture the buckling phenomena and the ovalization phenomena using VAM. But since it is a nanostructure, we need to also take into account the material length scale parameters, the small scale effects as well. So that is why now we are moving on to the strain gradient theory, which is given by Minton. And yeah, they contain the higher order strain terms, which are the derivatives of strain. So these are the additional strain gradient terms which are included in the strain gradient theory. The dilatation gradient vector, which is the differential of the gradient of the dilatation strain. Then we have the deviatoric stretch gradient tensor and the symmetric rotation gradient tensor. And each of these strain gradients have a corresponding strain tensor. So here is where we include the material length scale parameters. So L0, L1, L2. I think this will be L2, so that is mistake. So these are the three material length scale parameters which was given by Lamb. So these are basically the parameters which define how much the smallness of the structure affects the behavior in the mechanical framework. So again, now we want to use the VAM formulation here. So we take instead of taking the classical strain energy expression, we use this modified strain gradient expression here. And again, we will do the order analysis for this strain energy functional. So currently we are studying a square cross-section beam. So here we have taken these small parameters, which is the width to length ratio, and a new small parameter because of the inclusion of the material length scale parameters L0, L1, L2. So we are taking L by the length also as a small parameter here. So now we are doing the minimization of strain energy functional again with respect to warpings to get the governing differential equations and applying these warping constraints to get the solution for this particular model. So coming to the length scale parameter, what is this length scale parameter? So these length scale parameters, they are additional material parameters introduced in the elasticity problem. They are similar to the Lame's constant used in classical elasticity, but they correspond to the gradient of the strain instead of the strain. So the physical meaning can be that it provides a representation of the area up to which the gradient effect is predominant. So that is what this length scale parameter it tries to give. Again, it is not a constant, meaning that it depends on the geometry as well as the material type. So it can be experimentally calibrated, and it has been experimentally calibrated for different materials like epoxy, copper, and nickel. So there are studies which try to get experimental results from bending and try to calibrate these results and get the value for these material length scale parameters. For example, for epoxy, it was found to be 17.6 micrometers. Then we take the beam thickness to be between 20 to 115 micrometers. And these are again some examples of material length scale parameter for copper wire. So again, now this is a circular cross section. So here the material length scale parameter, it depends on the diameter. So we have corresponding to different diameters, different value for the material length scale parameter. And then for nickel also we have such approximations as well. So some preliminary results, we have done a zeroth order solution and we have obtained the bending rigidity for square cross-section beams. So we were able to capture these length scale effects at the zeroth order analysis itself. And we see there is a beam stiffening behavior, meaning that the stiffnesses obtained, they are higher than those obtained by the classical results. So it means that if we go for a micro scale structure, the classical theory was presenting some bending stiffness, but in reality, it behaves stiffer to that results. So we obtained this 1D constitutive law, where you can see that for axial extension, the stiffness value is same as the classical. But for torsion, we have the L2 parameter here, which is additional. And similarly, for the bending, we have this stiffness expression, where this is the classical stiffness formula. And then we have L0, L1, and L2 corresponding to different additional stiffness terms. So using those results, we got the bending deflection of cantilever epoxy microbeam and for different beam thicknesses. So here we can see that we have obtained the results and for the R model as well as for classical model. So for epoxy, we are using the small scale parameter as 17.6 micrometer. And we are taking all the parameters to be equal as it is done in most literature. So we are following that. And for different beam thicknesses, for 20 micrometers, 50, 100, and 200 micrometers, we have obtained the deflections corresponding to the length to width ratio of the beam. So it is seen, if we go for the 20 micrometer beam width, there is a huge difference between the deflection results given by the classical model and the strain gradient model proposed by us. And as we increase the beam thickness, this difference, it starts to reduce. So it shows that as we move on to smaller length scales, we need to take into account these effects to obtain a correct or better approximation of the deflections. We also compared with the literature, Sahu et al. So we saw that we obtained the normalized bending rigidity against the width to the length scale parameter. So we see that the behavior is same and we have a very good correlation with it. Also, we see that the bending stiffness, it is dependent on the Poisson's ratio as well. So for one case of epoxy microbeam, we obtain this graph as well, where we plot the bending stiffness with respect to the Poisson's ratio. So to conclude, we have obtained a higher order beam model employing the strain gradient theory. And it shows that we can get an asymptotically correct model using VAM. We analyzed the bending behavior and as seen in literature, the stiffening effect was observed for our case as well. It shows that CONTINUUM models are not entirely correct for modeling micro or nanoscale structures. And as we reduce the width of the beam, that means as we reduce the length scale involved, means as we go for higher length scale, these effects do not have that much importance. And the bending stiffness dependency on Poisson's ratio is also observed. So the future scope is extending this strain gradient theory model to other beam cross-sections like strip-like beams or hollow tube-like cross-sections, and to study the effect of material length scale parameters on geometrically nonlinear effects as we did for CIT. So now if we also include these length scale effects, how will the geometrical nonlinearity and this material nonlinearity will come into play and how that effect will come? That is what we want to capture. And then moving on, we can study the buckling behavior of these higher order beams and extend the study to vibration analysis, including CNT-based composites in this study. So these are some of the references. Thank you.
So thank you. Very clear presentation. Was really easy to follow, even if it's a complex work, but it's very well presented and so much. I don't have any specific question, but a couple of curiosity. One, you verify your approach, non-traditional, non-classical approach with some theory that are in literature and so on. Why you did not verify with finite element?
It was shown.
It was one?
Yes.
Did everything.
This one, we have FEM methods as well.
So you did that?
No, with existing.
No, but you did not do any finite element model.
Actually, we have verified, but since like this is under review, so I have not presented all the results. We verified using shell elements and beam elements. Yeah.
And how is that correlation?
Yeah, so what we obtained was that for beam elements, there is an under prediction of the buckling loads. Sorry, for shell elements, they give a lower buckling load compared to our result because they take into account the cross-sectional deformation also. And for beam elements, since we are considering a straight beam without taking the cross-section closely, we have a higher level. So our model lies somewhere in between.
Okay, so that one with a beam is closer to the classical approach as you have them. Yeah. And the second curiosity, if you were here the first day, so we are doing some. I have a postdoc, a molecular postdoc that just finished last summer that implemented the carbon nanotube in the composite, and I saw that is one of the points that you put as a future work and so on. How you could use, if you have already an idea, maybe not, but this approach inside the composite. So you would implement the VAM approach, your non-classical approach inside the shell or inside the beam, the plate, or how you would?
Yes, so we can do both. Either we can go for homogenization, where we can have the safety and the composite. So we can
like the homogenization.
Start as it, or we can just take a plate, having sort of CND composites, and we can incorporate this higher approach for that plate or microscope. We can do.
You can do. So you do like two plates with this in the middle and then continuity, or?
I mean, I'm not sure how exactly it will be done.
Yeah.
I mean, I think that is something that is complicated, but we need to figure out.
But it's not your problem anymore because you will define students. Okay, thanks a lot.
Can you go back to that static validation slide 1 to 10? Yeah, this one. So the U and theta are the results of the 1D code, or are you obtaining
No, this is a simple population. So I did not show the simple being. Just a very initial guess kind of a word. Much into so
when you validate with the 1D, like when you validate with the beam results, are you using the 1D code or are you getting the recovery relations then using 3D displacements?
for this,
Yeah.
1D code is.
Can you go to the previous slide? Okay. In this one, when you have, like in point B, that you have the circular cross section, it's always constrained between the underformed shape. So it's like the perimeter.
No, actually, it's not constrained, but these are the shapes which we are getting from the formulation. So what we can see is as we are bending. So the main deformation of the cross section, it is occurring along this not an extension kind of behavior. That's why we are getting. We are not constrained.
No, but the perimeter of the circle reduces.
Yes. Just changing the shapes.